have on the test, but it is related to what you did in the laboratory. Okay. So again, a solution is a homogeneous mixture of two or more substances. You may recall the term homogeneous. Homogeneous means that you cannot separate the two components in the solution. They're evenly distributed in the solution. Now, the solution has two parts. It has the solvent, which is the major component of the mixture, and it has the solute, which is the minor component of the mixture. Another way to describe this is typically the solute is going to be the substance that changes its state of matter. Now, in an aqueous solution, that means that the solvent is water. As I mentioned in lab, we can talk about a solution as being a dilute solution or a concentrated solution. If we're talking about a dilute solution, we're talking about a relatively small amount of solute compared to the solvent. We're talking about a concentrated solution, we're talking about a large amount of solute relative to the solvent. But the problem with these terms is they're very subjective. It is dependent upon the individual whether you would consider it to be dilute or concentrated. So instead, we tend to talk in terms of molarity. Molarity is one of many units of concentration. Some of the other units of concentration include percent. So when you see that isopropyl alcohol is 70%, it means there's 70% of the, out of a milliliter, 70% of that will be the isopropyl alcohol. But molarity is going to be a very common term used in chemistry. And molarity is the number of moles of solute divided by the liters of solution. And so what we are going to do is we are going to be working with molarity today. We're first going to talk about molarity, get a better understanding of what molarity means. We're going to use molarity as a conversion factor, because this is a conversion factor that allows you to go between solute and solution. And we're going to talk about how you prepare solutions, either from a solid or from a liquid. And when we start talking about preparation of solutions from a liquid, we're going to talk about dilutions. And then we'll get into some solution stoichiometry. So in other words, we'll talk about using information about solutions in calculations involving chemical reactions. So, first of all, let's just talk about the meaning. Number one, you will notice that we use a capital M to represent molarity. Folks, I see students try to use M to represent moles. No, we don't use M to represent moles, because if you use M to represent moles, you may confuse it with the molarity. Instead, we use the term mole to represent moles. That way we don't confuse it with molarity. Molarity is represented by a capital M. So anytime I see this capital M, I'm going to take the molarity and I am going to divide it into its subunits. So this means that there's 2 moles of NaCl per 1 liter of NaCl solution. In the next one, I have 1.23 molar sodium nitrate. It means that there is 1.23 moles of sodium nitrate in 1 liter of sodium nitrate solution. So that is the meaning of that capital M. And it only takes a second to rewrite it into its components. And by rewriting it into its components, it becomes obvious that molarity can be used as a conversion factor because it has two unique units associated with it. Now, I do want to bring up something that we'll come up with more as time progresses, and that is this sodium chloride. Sodium chloride, if we add table salt to water, what happens to the table salt? It dissolves. And what happens when it dissolves is that table salt dissociates to form sodium plus and chloride minus. So we can take this 2.0 moles of sodium chloride per 1 liter of solution, and we could actually determine the molarity of sodium because the sodium chloride dissociates into 1 mole of sodium ion for 1 mole of sodium chloride. So in other words, the solution is also 2 molar in sodium ion, and it would be 2 molar in chloride ion. We could do the same thing with the sodium nitrate and we would get a similar result. I want to do one more with you though. I want to do calcium chloride. Let's say I have 0.075 molar calcium chloride. That means that I have 0.075 moles of calcium chloride per 1 liter of solution. Now, calcium chloride is a little different than sodium chloride because when calcium chloride dissociates, it does so to form a calcium ion and 2 chloride ions. So if I look at the chloride concentration, I started out with 0.75 moles of calcium chloride per liter of solution. Well, if I want to know the concentration of chloride, there are 2 moles of chloride per 1 mole of calcium chloride. And so we're talking about 0.15 molar. Yeah. So it's 0.15 moles of chloride in 1 liter of solution, or in other words, it is 0.15 molar in chloride. So 2 things that are brought up, well, 3 things that are brought up here. Number 1, take the time and rewrite that molarity. That capital M stands for moles over liters. The second thing that I brought up is that when we're dealing with ionic compounds, at least the ones that I'm talking about at this point, can dissociate into their ions. We'll talk about more, we'll get to more about who dissociates on Monday of next week. But it dissociates into their ions. We can use this dissociation to figure out how much of an ion is present in solution using the mole-to-mole ratio. Questions? So let's look at another example. If you dissolve 25.5 grams of potassium bromide in enough water to make 1.75 liters of solution, what is the molarity of the solution? If I want to know the molarity, that means I'm going to need moles of solute, in this case KBr, per liter of solution. So I need to get those two pieces of information so I can do this math. So I'm going to take that 25.5 grams of KBr, and how do I convert a mass into moles? You use the molar mass. 79.9. The molar mass for KBr is that it is 119 grams per 1 mole. So therefore, we're talking about 0.214 moles of KBr. Keeping in mind that I was asked for the molarity, I need moles. Okay, I have the moles. That's 0.214. And I need the volume of solution. I was given the volume of solution. That's 1.75 liters of solution. So therefore, we're talking 0.122 molar KBr. Basically, folks, these first few problems is all about knowing the definition of molarity, or the formula, I should say, of molarity. The formula is moles of solute over liters of solution. Whether you're taking the molarity and dissociating it into its components, or whether you're calculating the molarity, you're using the equation molarity is equal to moles of solute over liters of solution. So how do we make a solution? There is a proper technique, and it's not just taking it's not getting your volume of 1.75 mils and adding the 25.5 grams of KBr. If you do that, your volume of solution is not going to be 1.75 mils. Again, when we're talking about this, we're talking about the amount of solute in a specific volume. We're not talking about changes in volume. So this is an example where they're using cobalt 2 chloride dihydrate. They take the cobalt 2 chloride dihydrate and they mass out the quantity that they needed. Then they add that quantity of solid into an Erlenmeyer flask. I mean, not an Erlenmeyer, a volumetric flask. Volumetric flasks are designed to hold a single volume. So you pick the volume that you need. In this case, they picked the 500 milliliter volumetric flask. They added the solid to the volumetric flask. They then added a portion of the water. Well, in this case, they're using ethanol as the solid. They added a portion of the ethanol. They then shake that up, stir it up, so that all of the solute, the cobalt 2 chloride dihydrate, is dissolved. This way, you can guarantee the volume, because then you add more solvent until you get to the mark on the volumetric flask, and that will give you an exact volume of your solution. So this is the way we would have prepared that KBR. In the case of the KBR, we would have taken the 25.5 grams of KBR. We would have masked that out. We would have added it to a 1.75 liter volumetric flask. We would have added some water to that volumetric flask to dissolve that 25.5 grams of KBR. And we would have dissolved it well. We would have then capped it off at the 1.75 mark so that we would have exactly 1.75 liters of KBR solution. Now, as I keep saying, I've said it in lab and I'm saying it here, molarity can be a conversion factor. It is a value that allows you to move between moles of solute and liters of solution. If you divide the moles of solute by the liters of solution, you get the molarity. If you divide the moles of solute by the molarity, you will get the liters of solution. And if you multiply the molarity by the liters of solution, you'll ultimately get the moles of solute. It's a conversion factor. You can use this diagram to help you figure out how to do the conversion, or you can just understand that it is a conversion factor like every other conversion factor that we have used to this point. It is a fraction that has a numerator and a denominator. Personally, I find the latter to be the easier to think about because I don't want to memorize a gazillion things. So I find it easier personally to think about the fact that molarity is a fraction. It is moles of solute over liters of solution. Whether I use that molarity as moles of solute over liters of solution, or whether I flip that molarity to be liters of solution over moles of solute is dependent upon what I need to ultimately get rid of in my calculation. So let's look at an example. How many moles of solute are required to make 3.0 liters of a 2.0 molar solution? I have 3.0 liters of solution that is 2.0 molar in concentration. What that means, again, every time I see that capital M, I take and rewrite it. So that means it's 2.0 moles of solute per 1 liter of solution. By rewriting that to represent the subcomponents of the molarity, I can see that it is a conversion factor. I can see that I need to start with the 3.0 liters of solution because that has only 1 unit associated with it, whereas molarity has more than one. So I begin my calculation with the 3.0 liters of solution. Now, I need to get rid of liters of solution, so I need the liters of solution to be in the denominator. That's awesome because that means that the molarity is already in the form that I need it in. So I'm going to write the 2.0 moles of solute over 1 liter of solution. The liter of solution will cancel, leaving moles of solute, and therefore you can calculate the fact that you need 6 moles of solute. Let's look at another example. What mass of KBr do you need to make 250 milliliters of a 1.5 molar KBr solution? Okay, so we are given 250.0 milliliters of solution. And we are given the fact that this solution is 1.5 molar KBr. I am going to take that short amount of time to rewrite the fact that that molarity means it's 1.5 moles of KBr over 1 liter of solution. By rewriting the molarity into its components, I can see which piece of information I need to start the calculation with. In order to start this calculation, I'm going to begin with the 250.0 milliliters of solution. I am starting with that particular piece of information because it has only 1 unit associated with it. Now, molarity is the only way to go between solution and solute. In order to use the molarity, I need the volume in liters. So my first conversion is going to be to convert that milliliters of solution into liters of solution using the fact that there is 1,000 milliliters per liter of solution. The milliliters cancel and I'm left with liters. And now I can use that molarity. That molarity is 1.5 moles of KBr per 1 liter of solution. The liter of solution had to be in the denominator so that the unit and the substance would cancel, and I'm left with moles of KBr. But I wasn't asked for moles of KBr. I was asked for mass of KBr. So therefore, I'm going to need to use the molar mass to convert the moles of KBr into mass of KBr. With 119 grams of KBr is equal to 1 mole of KBr. The mole portion went in the denominator and the mass in the numerator. And now I'm ready to do this math. And you get 44.6 grams of KBr, which if we're focused on significant digits would give us 45 grams of KBr. That means we need to take 45 grams of KBr, add it to a 250 milliliter volumetric flask, add some water, swirl it around, then top it off at the 250 mark so that we can get an exact 1.5 molar solution. Questions? Let's look at, let me give you an opportunity to do this one. I'll give you the molar mass here in just a second. The molar mass of glucose is 180.18 grams of glucose is equal to 1 mole of glucose. This problem was almost identical to the last problem. Again, I identify what I've been given. I've been given 0.55 liters of solution. That is 0.100 molar in concentration. Because that is the capital M, I dissociate that into its components. So it's 0.100 moles over 1 liter of solution. So I start with the 0.55 liters of solution because I'm always going to start with something that has only 1 unit associated with it, if at all possible. The liters of, then I use the molarity, and I used it in the format that it was written because I needed to cancel out the liters of solution. That left me moles of glucose, but I was asked for the mass of the glucose. So therefore I took and multiplied it by its molar mass so that the moles of glucose would cancel out, leaving mass of glucose. And then I did the math and got 9.9 grams of glucose. Questions? So I said there were 2 ways we can make a solution. The first is we can start out with a solid, and we can dissolve that solid to make a solution. The second way is we can perform a dilution, where we start out with a stock solution, which is simply a solution that is more concentrated than what we need. And then we dilute that concentrated solution down to the concentration we want. An example is the fact that if I were to look for concentrated hydrochloric acid, I would be getting 12 molar hydrochloric acid. But in the laboratory, we don't tend to use anything of over 1 molar if we can avoid it. So we go ahead and take that 12 molar concentrated hydrochloric acid and we dilute it down to the 1 molar. Now, how do we perform a dilution calculation? Well, you may actually already be familiar with a dilution calculation if you've had biology. In biology, you may have seen C1V1 equals C2V2, where C stands for concentration and V stands for volume. We're using the same equation, except we use M1V1 equals M2V2 because 99% of the time in chemistry, our solution concentration unit that we're going to use is molarity. So all we're doing is specifying our unit of concentration. Now, you're going to hear me probably repeat this. The only time you use this equation is if you're talking 2 solutions and the solute is the exact same substance. Again, the only time you will use this equation is if you're talking about two solutions and the solute is the exact same substance. In fact, if you use this equation to do solution stoichiometry, which we'll talk about next, you will get your entire problem wrong, and I have no problem counting every single point off. The only time you will use this equation is if you're talking two solutions and the solute is the exact same substance. So let's look at an example. A procedure calls for the spherification or I should say a procedure for spherification, making a sphere. Calls for 3.00 liters of a 0.500 molar calcium chloride solution. How can we prepare this solution from a 10 molar stock solution? Well, if we're talking a stock solution, we're talking about the same substance. So we're going to use the equation M1V1 equals M2V2. Now, it does not matter which solution is M1 and which solution is M2. What matters is that you keep the appropriate pieces together, and that's what that word of is telling you, is that these pieces of information must stay together. So I'm going to say M1 is equal to 0.500 molar. V1 is equal to 3.00 liters. M2 is what I want to solve, or no, is 10.0 molar. And I want to solve for V2. So that will be 0.500 molar times 3.00 liters is equal to 10.0 molar times V2. Solving this equation, you get an answer of 0.600 liters, or in other words, if you want to put it into milliliters, we're talking about 600 milliliters of solution. So what does this calculation mean? It means we measured out 600 milliliters of our 10 molar stock solution, and we added it to a 3-liter volumetric flask. We then added water to the mark and swished it. And what came out was we made a 0.5 molar solution that is 3 liters. That's what that calculation tells us is, again, we had 600 milliliters of our stock solution. We added it, and this isn't the exact calculation. We added it, and we diluted it to the 3 liter mark. No, it is the exact, and I misdid the math. That should have been, oh, I misdid the math. The setup is correct. But the answer should have not been 600 milliliters. It should have been 0.150 milliliters. Yes.
Which side of the equation you put the values on, or as long as they're paired together?
As long as they're paired together, it doesn't matter whether you call the stock solution M1 or whether you call the solution you want to make M1. As long as the of, which says keep that together, as long as those stay together, it doesn't matter which side of the equation it's on. Questions? Yes.
I'm wondering if I'm okay.
No, I was trying to do two things at one time and I didn't succeed on either one. You can tell I don't write this stuff down. Otherwise, I would move faster. That's the problem with me writing stuff down, is I'll move much faster. Okay, let's look at one more example to what volume should you dilute 0.200 liters of a 15 molar sodium hydroxide solution to obtain 3 molar. Again, the of says keep me together. Let's see if I can do this one without making an error. So M1, V1 equals M2, V2. I'm allowed to use this because I'm starting with sodium hydroxide and I'm ending with sodium hydroxide. What volume, okay, would I dilute a 2.200 liter of 15 molar solution to obtain 3.00 molar? So V1 times 3.00 molar is equal to 15.0 molar times 0.200 liter. You get a V1 of 1. That will be in liters because the molarities have canceled, leaving liters. What does that mean? What it means from a action perspective is we would have taken 200 milliliters of that higher molarity solution, and we would have added that to the volumetric flask. We would have then diluted that with water to the 1 liter mark, and what would be left over would be a 3 molar solution of sodium hydroxide. The image at the top represents a specific little volume. In other words, it's like I'm looking in a microscope. A 500 milliliter aqueous ethanol solution. If I add an additional 500 milliliters, meaning I've doubled the volume, which one of these would represent that little bitty sample? A, B, or C? All those that think C. All those that think A. All those that think B. It is C. I doubled the volume, so I would half the amount of molecules in that same little cell. I understand that it's difficult to think of solutions. It's easy to think of a mass. You've seen a mass. You've dealt with mass. You've done stuff with solids upstairs. You've you've weighed yourself on and off all your life. It's easy to think of mass, but it is much harder to think of what's going on in a volume of a solution. Which is what you're being asked to do. So far, we've talked about the meaning of molarity. Molarity is moles over liters. We've looked at how to calculate the molarity. You get the moles, you get the liters, and you put it moles over liters. We've looked at how to use molarity as a simple conversion factor. Molarity can be written as moles over liters if I'm needing to get rid of liters. Or I could flip the molarity so that it's liters over moles if I'm needing to get rid of moles. And we've looked at dilutions. Dilutions are simple. It's M1B1 equals M2B2. But the starting solute and the ending solute have to be the exact same substance. Now, we're going to get into some more reaction stoichiometry, but we're going to deal with solutions as part of our stoichiometric conversions. Again, molarity represents a conversion factor. Capital M is moles solute over liters of solution. It is a fraction. Fractions are conversion factors. Again, if I have liters of solution, I can use that molarity in order to convert it into moles of solute. But if I have moles of solute, I can still use that molarity as a conversion factor. I just have to flip it on its head. Again, going back to the diagram the flow chart I gave you. We've taken the number of particles, ions, atoms, molecules, and we've used Avogadro's number to get that to moles. We've dealt with mole-to-mole ratios. The mole-to-mole ratio can come from two locations. If you're dealing with stoichiometry, it comes from the coefficients of the balanced chemical reaction. We've dealt with density as a conversion factor and mass, the molar mass, as a conversion factor. Again, ultimately getting us into moles. We are now going to finish this flow chart because now we have molarity as a conversion factor used in stoichiometry that will allow us to go from volume of solution into moles of that solute. Let's look at this in practice. What volume in liters of a 0.150 molar KCl solution will completely react with 0.15 liters of a 0.157 or 0.175 molar lead to nitrate solution according to the balanced chemical reaction? Okay, let's break this down. We've been asked what volume in liters of KCl that is 0.150 molar in concentration will completely react with 0.150 liters of a 0.175 molar lead to nitrate solution according to the balanced chemical equation. As I mentioned on Monday, when we're doing stoichiometric calculations, we are not going to start the calculation with the material we have the question about. Therefore, we're going to start this calculation with the lead to nitrate. Now, if you don't take time to do the next step, this is where a lot of students make their mistake because they don't know which unit to begin the calculation with. But if you take time to rewrite that molarity, it becomes blatantly obvious that you should start with the 0.150 liters of solution because that has only one unit associated with it. So we're going to start our calculation with 0.150 liters of PbNO3 solution. Our first conversion factor is going to be the molarity of the PbNO3 because that will allow us to go from liters into moles. The liter portion will go in the denominator and the mole portion in the numerator. we put the liter portion in the denominator so that the units would cancel, leaving moles of PbNO3 We now, because we have it in moles, we are allowed to convert from one substance into the next substance using the mole-to-mole ratio, which is 2 moles of KCl is 1 mole of PbNO3 And that converts it into KCl, which is the substance we have the question about. Now we have been asked, what is the volume? Again, knowing that molarity is moles over liters shows you that the molarity is a conversion factor. In this particular case, I need the moles in the denominator. And the liter will go in the numerator. The moles had to go in the denominator so that they would cancel. And when you key this into the calculator, you get an answer of 0.35 liters of KCl solution. If you go back to our flow chart, we wanted to go from volume of PbNO3 to volume of KCl. We wanted to go from volume of PbNO3 to volume of KCl. Our first conversion factor was the molarity of PbNO3. The second conversion factor was our stoichiometric mole-to-mole ratio. Our third conversion factor was the molarity of KCl. Let's look at another example. What molarity of zinc chloride forms when 25.0 grams of zinc reacts with copper chloride according to the following reaction? Assume the final volume is 275 milliliters. We have been told that we have 25.0 grams of zinc. We have been asked to determine the molarity of our zinc chloride. And we have been told that the final volume is 275 milliliters. Okay. We want molarity. We want moles, in this case of zinc chloride, over liters of solution. We never start our calculation with the substance that there is a question about. Therefore, we're going to start our calculation with the zinc. So 25.0 grams of zinc. We're going to start by converting that into moles of zinc with the molar mass of zinc, which is 65.38 grams, is equal to 1 mole. The grams go away, leaving us moles of zinc. Now we can use the mole-to-mole ratio. 1 mole of zinc results in 1 mole of zinc chloride. The mole of zinc went into the denominator so that the unit and the substance would cancel, and we're left with moles of zinc chloride. I all of a sudden have the numerator. Which is 0.382 moles of zinc chloride. I just need the denominator. And I know that the amount of solution was 275 milliliters. Converting that into liters, that is 0.275 liters of solution. So I can put that into my denominator, and I get a molarity of 1.39 molar zinc chloride. And I just only have so much paper, so, or tablet. Folks, we can go back to this. I started out with 25 grams of zinc. My first conversion factor was the molar mass of zinc to get it to moles of zinc. My second conversion factor was the stoichiometric factor, or the mole to mole ratio, to get it from moles of zinc into moles of zinc chloride. Now, ultimately, I wanted molarity. Well, molarity is moles over volume, and so that's where the molarity came from. Let me give you this one to do. I'll see if I can blow it up a little. There we go. Yes.
Where it has milliliters, the problem, do we need to bring the final, like, answer back to milliliters, or can we leave it?
Okay, so that's a great question. It depends upon if I ask for it. I would have accepted either one of these answers because I didn't specify in the question. That's why I gave both, just in case you went back to milliliters, though it wasn't required. Okay, so basically, I listed out my information, and the thing I had the question about was sodium phosphate, so that's why I didn't start with the sodium phosphate. I started with the copper 2 chloride. I took the 80, and then the other thing I know is that means that these two pieces of information, the 82.9 milliliters and the 0.121 molar, go together. So I took the 82.9 milliliters and I converted that into liters so that I could use that 0.121 molar, which I broke into its units, to convert that into moles of copper 2 chloride. I then used the mole-to-mole ratio from the balanced chemical equation to convert the moles of copper 2 chloride into moles of sodium phosphate. And now that I have it in moles of sodium phosphate, I can use the information about the sodium phosphate, which is the molarity, to get it into liters. But in order to use the molarity of the sodium phosphate, I had to flip it on its head, so that the moles were in the denominator, so that those would cancel out, leaving liters. And I got 0.0446 or 44.6 milliliters. Questions? Okay, so what we did today is we have really started using molarity, which is a unit of concentration, to talk about solutions. We've done the mathematics so far of solutions, which is understanding what molarity means, using molarity as a conversion factor, dealing with molarity in dilution, using molarity in the case of a stoichiometric reaction. On Monday, I need to explain next week, and then I've got a surprise, or I don't have a surprise, Elian has a surprise. On Monday, come prepared to take some notes, because we're going to go ahead and start talking about solutions in greater detail, specifically associated with ionic compounds. We're going to deal with electrolytes. We're going to talk about the different types of chemical reactions. And we're going to talk about precipitation reactions, which is pretty much one half, roughly, of what you're going to have to do in the lab, with the lab. The lab itself is fast. It's a matter of drop, 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 look and see what happens. It's the actual doing the post lab that is a challenge. And so that's why we're going to get into that discussion, so that hopefully on Thursday of next week, I can discuss precipitation reactions, acid-base neutralization reactions and redox reactions. Couple more things about lab. Number one, don't forget your molarity lab or the titration lab you did this week is due on Monday in lab. Number two, The next lab, the reactions lab that you will be doing on Monday is actually gonna be turned in using, Active. So this morning, two things came available on Active. One is the homework, which has problems of today and problems of Tuesday. One of them is the reactions lab, and it's stated as reactions lab. You're not ready to do that one. That one we've got a couple of weeks on. So just leave it alone for now. Once you do the actual lab, going in and plugging, you'll be able to go in and plug and chug from what you write out in the lab into Active to finish out that reactions lab. But I'll explain more on Thursday of next week. So again, we're not ready for that, but there are two things that came up today on Active. Just worry about the homework. Ian, it's now you.
So the good news is I'm gonna redo what I did last exam tomorrow. There's something 2 SI sessions. Purely over exam review, practice problems that are very similar to what's gonna be on the exam. Also make slides and then your excuse for the exam, I'm gonna send out after this class period. So if you feel you need help, I will come tomorrow. In the email, I'll have the times, but they're roughly the same times that I did last time, 2 to 3. And I only changed the last time from 6 to 7 to 5 to 6. So yeah, if y'all need help, be there, I'll be there to help y'all. And that's tomorrow, same room as every other SI session I posted.
So there's 3 SI sessions between now and the test. 2 to 3 tomorrow, 5 to 6 tomorrow, 5 to 6 Monday. All in preparation for exam 3. And then next Tuesday, we've already talked, and Elian will be doing problems associated with what we did today. Any questions? Not, I will see you and good luck on your exam. I'll see you Monday in lab. All 72 people. And if you didn't pick up your stuff on Tuesday, come grab it. It's alphabetical.